Hello and welcome to Control Delete Tutorials. My name is Jason, and this video is going to be perfect for you if you're doing the AP Computer Science Principles exam and you forgot how to do anything dealing with binary and ASCII and decimal and hexadecimal. So this is going to be like a crash course, so we're just going to jump right in. So let's start off talking about decimal, okay? So decimal is a base 10 system, which means that each place value is 10 times bigger than the previous one. So if we look, this is our normal number system, by the way. This is the number system we use for everything. Our number system is base 10. So you have the ones place, the tens place, the hundreds place, and the thousands place. Each place can have up to 10 digits from 0 to 9. Counting 0, that would be 10. So for instance, if I did this, I have 1. Okay. If I had a 9 here, that would be 9. Pretty tricky already, right? Okay. If I put a 5 here, okay, now I've got 59. Okay, we're not worried about these zeros because 0 means I don't have hundreds, I don't have thousands and 10,000s, whatever, so on. It keeps going up. I'm just using these 4 to start with. Okay, if I have a 2 here, now my number is 259. So I have 9 ones, 5 tens, 2 hundreds, and let's throw in a 6 just to keep them honest. 6 thousands, 2 hundreds, 5 tens, and 9 ones. That's base 10. That's basically it. We refer to this in computer science as decimal. That's just the name for it. Doesn't mean like 5.678, not that type of decimal. We're talking about decimal as in the base 10 number system. Not a whole lot I have to say about this system because everyone should be pretty familiar with this. So get used to this because this is going to basically translate to all the other systems that we have. So if this one is base 10, that means we can have 10 numbers that go here, 10 numbers that go here, 0 to 9. I can only display one at a time. I can't put a 10 in here. That's 2 digits. I can only have one number in here at a time. I can't have multiples. That also is very important. So I can have some number of ones. So 10 digits go here. Each place value goes up by 10. That's it for decimal. We can kind of come back to decimal because we can convert our other number systems to decimal. So we'll look at that as well. Okay, that's decimal. Let's hide that boy. We'll come here to binary. Okay, this is binary. Guess what? It's base 2. Okay, which means each place value, so this is the 1's place, the 2's place, the 4's place, 8's place, 16's place, 32nd's place, 64th's place, 128th's place. I don't know if I'm saying those correctly, but those are the place values. So just like we had a 1's place and a 10's place and a 1000's place, these ones, the numbers go up by 2's. Okay, I don't want to click on that. Okay, so they go up by 2's. Okay, that also means that I can only have 2 digits that go in each place value. So in here, this would be a 0 or a 1. Those are the only 2 numbers I can have in every place. So just like when we were dealing with decimal, here I can have 10 digits because I'm dealing with base 10, and I can go from 0 to 9. That's 10 different numbers. Okay, if I go back to binary, and let's hide that there. Okay, so 1's place up to 128's place. That means that binary has a range, and you can see the range actually is easy to figure out, even if I don't know, my numbers very well. Okay, each one goes up by another number. So from the 4's over, this can only add up to a total of 3. If I need 4, I have 4 here. These added up together would be one number less than this. So these added up would be 7. These added up would be 15, okay, because we're 1 less than 16. These added up would be 31. These added up would be 63. And these added up would be 127. So that means if I added all of these up, my next number, if I'm looking at the pattern, each one goes up by 2, my next number that would be here is if I had another bit, which is what we're talking about, bits of information. the next number would be 256. So that means I can count from 0, because if this is a 0, it means I have 0, 1, 0, 2, 0, 3, 4s, 0, 8s, 0, 16s, 0, 32nds, 0, 64, and 0, 128. So if I had a 1 in all of these, let me change these over to a 1. Okay, my range here, okay, I'm not going to change all these, but if these were all 1s, then it would be 1 less than the next number in the pattern. And so if we had 256, that means I can go to 255. So 0 to 255 is the range for binary, base 2, if we're dealing with 8 bits. So what we have here is each of these represents a bit of information, okay? And each one is either 0 or 1, okay? Because I can only have 2 digits, 0 or 1. Okay, so that means that if I'm dealing with binary, and I said a number, let's say I do, because of easy math. Okay, so let's say my binary number is 10000010. Okay, so I add up my place value numbers, basically meaning if I have a 1 in any of these place values, I have that number. If I have a 0, I don't have that number. Just like when we were talking about decimal. Okay, if I have a 1, I have 1 1. If I have a 9 here, that's 9 ones. But binary doesn't allow 9s, okay, because it's only 0s and 1s. So I add up my numbers here. 128, I have 1 of those. I have none of these. I have 1 2. 2 plus 128 equals 130. Okay, I tried to do that for easy math and I still screwed it up anyway. Okay, looking back at decimal, just so we have a comparison. If I have 1 1 and 5 10s, added up, that's 51. If I have, if these are zeros, okay, meaning I have 0 thousands, 0 hundreds, 51. Okay, so same idea, but we're applying it to zeros and ones. I have a 128. I add it to 2. I get 128 plus 2. I get 130. Okay, so these are the place values of the numbers. Let's do one more just so we make sure we know what's going on. And we'll show how this works with the other number systems. Okay, so let's say we take 64, and we have 1 of those, and we take 1 of these. Okay, so we have 1 1 and 164. That's going to be a decimal value of 65. Okay, so when we add these up, we convert that to a decimal value. That's what the value is. So we're getting, because these are all decimals, each one of these is essentially a decimal. Okay, 16. I have 110, 16. That's a decimal value that's shown at the top. So when I add these up, I get a decimal value. Okay, now we're going to come back to binary in just a moment, but I want to look at another number system. Let's go to hexadecimal. So hexadecimal is a base 16 number system. So that means each position here, each place value, I have a 1's place and I have a 16's place. Okay, but I told you before, I can't have this. Okay, I can't have 2 digits in here. And you'll notice this goes from 0 to F. Now, that's kind of weird, right? So let me come back here. So that means that I can have my normal 0 through 9, but to represent 10, 11, 12, 13, 14, and 15, I have to use letters because I can only have 1 character in here at a time. So if I have A, that's a 10. So if I have an A here, that means I have 10 1s and 0 16s. Now, why does it go up to 15? Well, the same reason the other ones. Okay, if I go to binary, I can have from 0 to 1. I have 2 numbers that can go there. This is base 16, goes from 0 to 15, 16 total digits that can go here. So how do we figure out decimal values of hexadecimal? I'm glad you asked. Okay, so let's say I've got a 10 here. Okay, can't put 10, so I put A. And let's say I've got a, let's do C. Okay, so that is my hexadecimal value. Oops. AC. All right, well, how do I figure this out? This category is take this number and multiply it by 16. Okay, so if I were to do that, let me just draw it out. Ooh, I'm going to make myself do math. Crazy. Okay, 16 multiplied by A, which is 10. Okay, I did that on purpose, so it's one I can do in my head. 160. Okay, so I have 160. And on this side, how many ones do I have? I have 12 ones. So I take 160 and I add 12 to it. Okay, 160 and 12. Okay, got it. 2, got a 7, got a 1. 172, that's the decimal value of this. Okay, so I have the decimal value 172. Now here's what's kind of cool about this. Hexadecimal we use all the time. It's a specific reason I made this entire thing in Photoshop. So, if I go here, you can see that I've got colors here. So this is my hexadecimal code. Okay, 1200FF. Now you'll notice FF, this is my blue channel of color. This is green, 00, and this is red. And you'll notice here, these are my decimal values of those. So if I put in 172 for any of these, let's go to the green channel. 172, and you'll notice we get AC, which is what we started with here. Okay, AC is 172. Okay, if I put in 18, I should get 12. So let's do that. So you're going to get confused and go, but 18 is 18. No, it's not. That's not how that works. Okay, so I do, what did I just say, 18? What number did I have? I have a bad memory. Okay, 18 here, that's 1 and a 2. Okay, so 1 and a 2. Okay, if we do this, let's delete our stuff here. Alright, let's get rid of all of my notes here for a second. Okay, so we're doing 12. Okay, 12 times 16. Wait, no, that's not what I wanted. Okay, so I have 12. Okay, this one is going to get multiplied by 16. 1 times 16, luckily that's 16. And 2. Alright, that's a nice easy one. That gives us 18. And look, the color value for red here was 12. And the value, the decimal value, was 18. That's crazy. Okay, 255. Okay, 255 is FF. Okay, hexadecimal, ooh, that was loud. Hexadecimal also has a range of 255. Now you're probably saying, well, why don't we just use binary and decimal then? Well, because look, I can have this with just 2 numbers instead of 8 numbers. Okay, so F is 255 and 0. So this would be F being 15. 15 times 16 is 200 and something. And then 15, so it's like 240, right? Plus 15 would give me 255. My math correct there? Okay, that is hexadecimal. Okay. Could not. I'm not on the right layer. Boop. Okay. Now, where do we go next? ASCII. This is an ASCII chart. Here you can see the decimal value. So there's my decimal values. Stop clicking. Okay, decimal values and hexadecimal values. Okay, decimal, hexadecimal. Here we have characters. Okay. So The characters, also referred to as glyphs, are what keys do these equal, or what commands do they equal on a keyboard or to a computer. Okay, but the ones we're worried about, I'm going to do some super magic here. Boop. Okay. So what we're looking at are just these two rows. The letters capital A through capital Z, or uppercase A through uppercase C, and lowercase a through lowercase c. Okay, we're just looking at those ones for now. Don't worry about the other ones. And why do I have all this other stuff up? Okay, so the decimal value, let's fix that up a little bit so we can read our chart a little better. There we go. Okay, so our decimal value, 65, converts to the ASCII character A. Okay, if we go down here, the capital or uppercase Z is 90 in decimal. Okay, we're not really so worried about hexadecimal right now, but we could focus on that later. Okay, and then here we have from 97, just clicked on something there. Okay, from 97 for a lowercase a to 122 to a lowercase z. Now you'll notice 65 and 97 are exactly 32 apart. That's important. Why is that important? So if we look at the way they've done this, we can get the decimal value from binary and convert it to ASCII characters. Okay, these characters here. So to do that, we could look at a chart. So I could get the binary. So let's say I had a binary here. I'm going to write it in because it's going to be harder to do otherwise. So let's say I had binary. So let's say I had 0. Oh, that's not a 0. 0. There we go. 1. And we're just going to leave this 32 blank for a second. And let's say these are all zeros. Writing with a mouse is easy. And this is a 1. So these first 3 digits, we have a way of easily seeing what letters and what letters and characters we're converting from, based on whether we're going from binary to ASCII. Okay, so from binary, 0, 1, something, 0, 0, 0, 0, 1. So if I look at just these first 3 bits, the first 3 bits on the left, if it's a 0, 1, 0, so there's nothing here. Okay, if that's 0, 1, 0, that's going to be an uppercase letter. Okay, notice 32 is the difference here. If I have 0, 1, 1, that's a lowercase. The difference being 32. Okay, 65 and 97. That's a difference of 32. The difference being 32. Okay, so these first 5 bits on the right are going to be the letter index. Which letter of the alphabet is it? So if I have 0, 0, 0, 0, 1, that's the first letter of the alphabet. If we look here, 0, 1, 0, 0, 0, 0, 0, 1, okay, is the first letter of the alphabet. This would be uppercase A, okay, if it's 0, 1, 0. Now, all we would really have to know here is this means uppercase, and I don't want to erase, but I guess I'll have to. I could delete, I guess. Makes it a little easier. Okay. So if this is 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 1, that would be a lowercase letter a. Again, the difference just simply being this 30 seconds place. What? Go away. Okay, so if we add them up, if we did it the hard way, and we needed to look at a chart for this, 64 plus 1 is 65, 65 uppercase A. if I change this to a 1, it's going to be 64 plus 32 plus 1, which gives me 97, which is a lowercase a, which is exactly what I said. So if we didn't have this chart in front of us, oh, that looks bad. Okay, we're going to keep the chart there. Okay, so if we didn't have the chart in front of us and we had to figure out from binary to letters of the alphabet, let's say I wanted to get the letter C. Okay, so let's say we're doing a lowercase letter C. So 0, 1, 1, okay, that's lowercase, and a letter C. Well, C is, so you have A is the first letter, B is the second letter, C is the third letter. So let's change this one. Let's delete this and change it to this. Okay, 2 plus 1 is 3. Okay, we have a 2, we have a 1. 2 plus 1 is 3. That gives us the third letter of the alphabet. Lowercase, letter C. Okay, these ones tell us the letter, these ones tell us the case, uppercase or lowercase. I feel like I'm saying this a bunch, but okay. Let's do a Z. Okay, we have Z on the bottom there, but let's pretend we're not looking at that. Okay, let's get rid of those. Okay, so we want uppercase, letter Z. Okay, uppercase 0, 1, 0, and a letter Z. Okay, so letter Z. Letter Z would be the 26th letter of the alphabet. Okay, so we're going to need a 16 for sure to get up to that number. Okay, how do we get to 26 by adding these up? 16, yep. Okay, so we need 10 more. 10 more would be there. And that means we don't need these guys. So 1, 1, 1, 0, 1, 0. If we look down here, I wrote 1, 1, 0, 1, 0 is 26. This would be uppercase. This would be letter 26. Uppercase Z. That's ASCII. Okay. So, using base 2, we can get back here. Now, here's the trickier thing. Let's say on the AP exam, they give us something like, they give us hex code. Okay, so this is something that could happen. Let's say we're given hex code. So we'll go back to hex here. Okay, so let's say they give us hex code 4 and actually let's do 2 because math. Okay, 2 and let's say 2D. Okay, so they're telling us we have to convert from hexadecimal to binary. So I'm going to walk you through the steps of how we would do that. First things first. First, we have to figure out what the hexadecimal, the decimal value of this is. Okay, so 2 16ths, that's 32. That's not too bad. Let's go to my notes here. So 2 times 16 is 32. I picked that number on purpose because math. Okay, D is 13. We're going to do some adding. Okay, that's 5. Okay, and that's 4. All right, our decimal value, so this is base 10, decimal 45. So 2D from hexadecimal converts to 45. Let's check that. If I put in 2D, okay, my red turns to 45. Okay, if we go here, 2D, my green turns to 45. If I go here, my blue, 2D, those are all 45s. That's a dark gray. All right, so 45. Okay, well, how do we get from 45 to binary? We haven't gone that direction yet. So we're going to, let's turn off hexadecimal, and we'll come back to binary. Oh, that makes it hard to see. Okay. All right. So, how do we do this? We start on the left. So let me just change all of these back to zeros. Okay. Oh, not double zeros. Okay, 0. Okay, so we look at 45 and we say, hey, can I subtract 128 from 45 and still have a positive integer? No, can't. Okay, so that means I have a 0. How about 64? Can I subtract 64 from 45? Nope. Okay, so that's a 0. Can I subtract 32 from 45? Oh, I can. So let's put a 1 there. And let's do what we just said. So we'll do 45. I just changed the color of my... I don't like that. Okay. So 45 minus 32. We had this from before. Okay, 13. All right, we go to the next number. 16. Can I subtract 16 from 13? I cannot. That's a 0. Can I subtract 8? You betcha. That's a 1. 13 from 8. Let's go back to our notes. 13 minus 8 equals 5. All right, can I subtract 4? Yes. If we're any good at math, we should be able to figure out the rest of it without having to keep subtracting. Okay, we have 1 left. All right, 1 left. All right, so our binary number from hexadecimal is 001, 0, 1, 1, 0, 1. Okay? That's 45. Okay, so that is decimal 45 still. Okay, if we add all those up, 32 plus 8 plus 4 plus 1 gives us 45. So that is how we get from hexadecimal. Oh, that looks great. So 2D, 2 times 16 is 32, plus 13 gives us 45. We take 45, put it in the binary chart, and just start removing numbers from left to right. And I think that kind of wraps this entire tutorial up. Let's see, anything else we need to touch on? We have decimal. Yeah, decimal's good. But yeah, when we're talking about binary specifically, binary, each of these are bits of information. So if you're told in the AP exam, which you will be, I have a, let's say a 8-bit integer. Okay, so if we're talking about an 8-bit integer, this will be the last thing. Okay, so an 8-bit int. Okay, how many numbers can you store in an 8-bit integer? Well, we can store from 8 plus 4 plus 2 plus 1, which means we can store from, come on, thanks ipsum lorem stuff. Okay, so 8 plus 4 plus 2 plus 1 is going to be 15, so we can store the numbers 0 to 15. Okay, so what does that mean? That means if they ask you on the AP exam, you have an 8-bit integer, and we know that can store from 0 to 15. We're not really worried about these numbers here. 8 bits means I can store this much information only. So 0 to 15 is all I can have. So then they say, what happens if you're given a math problem that can only store 8-bit integers? Let's change the size of my text here. Okay. So if you're given a math problem and they say, using 8-bit integers, somebody adds, let's say, 10 plus 8. And they get, let's do 10 plus 6. Okay? And they're surprised because the result is 0. Why would the result be 0? Well, I can't store the number, oh boy, I can't store the number 16, which should have been here, into an 8-bit integer. So we get what's called overflow. Okay? Which means that from 0, okay, so if I have only these numbers to choose from, that's 15. 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. If I only have these numbers to deal with, let's get rid of all that stuff. Leave me alone. Okay, and my notes is getting sloppy here. That's okay. All right, so if I can only store these numbers in an 8-bit integer, that would mean that if the number goes above here, I get overflow, which sends it back here. If this would have been 17, that means my answer here would have been 1, because it would have went 2 over this, 1, 2. Okay, that would have been 1. Okay, if I would have went 10, 10 plus 10, that would have been 20. So that should be 1, 2, 3, 4, 5. So it should be 4. If my math is right, which it might not be, but yeah. So if you're asked about 8-bit integers, you need to know binary for that. If it's a 16-bit integer, okay, now it can store from 31, so always go one number less because that's what all these add up to, which we talked about at the beginning. So go 31 to 0, that's 16-bit integers. I think that kind of covers everything. Was that a crash course? That felt really long. But anyway, if you have any questions, leave comments, and thanks for watching.